Epoxides, they undergo ring opening in presence of an acidic and basic medium. If we look at the epoxide are made up of sigma bonds between the carbon and the oxygen. And these bonds are very weak bonds. These are bent bonds. And the reason why they are bent bonds because of the angle strain of the epoxide. This is a 60-degree angle, which is a deviation from the ideal 109.5-degree angle. So this produces a huge angle strain. Together with the torsional strain, it makes those sigma bonds that are the overlap of the sp3 hybrid orbital of the carbon and the sp3 hybrid orbital of the oxygen. So these two orbitals, hybrid orbitals, they overlap, but because of the compression of these bonds, the sigma bonds are going to be bent because the hybrid orbitals are bent. This is going to make those bonds very weak, and these bonds, they can be broken easily. So this is why epoxide undergoes ring opening in presence of an acidic and basic medium. Now, before going into the reactions, we have to look at the charges on the oxygen and the two carbons. Oxygen is always more electronegative than the carbon. So oxygen will pull electrons away from the carbon, leaving each one of these carbons being an electrophile. This means that if there is a nucleophile in the solution, the nucleophile is going to come and attack the electrophile. Okay? Also, if there is an electrophile in the solution, then the oxygen, which is a nucleophile, is going to come and take the electrophile or attack the electrophile. Always your arrow needs to be from the more to the less, from the nucleophile to the electrophile. So let's start with the basic medium. A medium is said to be basic if there's no acid in the reaction. Then we say that the medium is basic. In the basic medium, I'm using those nucleophiles in here. Any one of those can do the job. So OH minus, OR minus, of course, these are coupled with metal, sodium or potassium. Sodium cyanide, ammonia, I can use Grignard, I can use alkyl lithium, I can use sodium hydride, any one of those. We said that the Grignards, they are carbon ions with a negative charge. So these are good nucleophiles in there, and these are good nucleophiles. Epoxides will not have an acidic hydrogen on it for this to act as a base and take the acidic hydrogen. So all of those will act as a nucleophile, and the nucleophile will attack the partial positive carbon. Now the idea here, which carbon is it going to attack, especially if you have an unsymmetrical epoxide? The rule for the basic medium is that when the base approaches or when the nucleophile approaches any one of those carbons, it needs room to approach. So in basic medium, the nucleophile is going to attack the less hindered carbon, meaning the less substituted carbon. Let's have an example over here. So let's say, for example, if I have the epoxide and my epoxide is occupying all the area over here, which is up, okay, and I am reacting this with sodium cyanide in presence of water. Okay, now my first step is going to be the sodium cyanide. My second step is going to be the water. So let's start with the first step in here. You always look at the first step to determine what type of medium you are working with. So if you don't see any acid in there, then this is going to be a basic medium. Then in this case, the nucleophile that you are using, it needs room to attack, so it's going to attack the less substituted carbon. So the nucleophile in basic medium is going to attack the less substituted carbon. My nucleophile here is the CN negative. So you have your C triple bond N, and this is your nucleophile from the carbon. Okay, now each one of these carbons here is going to be my electrophile. But we said that in basic medium, the nucleophile attacks the less substituted carbon, which is this carbon over here. This carbon has one carbon on it. This carbon here has two carbons on it. So this one is going to be the less substituted. After all, the nucleophile needs room to attack. But when it attacks, the nucleophile always attacks from the opposite side of the epoxide because it needs to break the bond of the epoxide. So it cannot come from the same side, it needs to come from the opposite side. So the reaction starts by the nucleophile attacking the less substituted carbon from the opposite side of the epoxide. So here the epoxide is up, then the CN is going to come from the back and open the bond. Now, because here I do have a rotation around the carbon, single bond carbon, the stereochemistry really doesn't matter a lot because see, if you go ahead and you break this bond, see, I'm breaking this bond over here. So if you break this bond, this oxygen will remain in front. It's going to retain the same configuration as the epoxide. So the oxygen here is going to remain in front. And now the CN is attacking from the back. It's going to be at the back. And I do have, of course, my CH3 over here. Let's go ahead and write the CH3 in plain there. And then I have my two ethyl groups. This is going to be a negative charge, but you guys don't forget that there is a free rotation around the carbon, single bond carbon. So whether I represent it like this, or if I go ahead and I represent it like this, it is the same. Because again, the oxygen and the cyanide, because of the free rotation, they can be on the same side, they can be on opposite sides. So if you don't have your epoxide locked in a cycle, then in this case, go ahead and just ignore stereochemistry and show it as I am showing it like that. I'll give you an example of how the epoxide is locked in a cycle in a moment. So now let's finish this reaction. It's a negative charge. So the second step over here is to do the protonation. And this is going to come, take the hydrogen, the OH is going to leave. This is going to act as a base. And this is going to be my acidic hydrogen in there. And my product is going to be an OH and the CN. Notice what did I do over here, okay? These are my two carbons of the epoxide. Let's go ahead and highlight them. So this is going to be 1 and this is going to be 2. These are my two carbons of the epoxide here. So these are my two carbons of the epoxide there. So what I did is I introduced the cyanide on 1, which is on the less substituted. And then the oxygen here was once belonging to the epoxide in there. So that oxygen now, the epoxide oxygen became an OH. Notice that the CN and the OH, they are adjacent to each other. So I know that there was an epoxide in this region over here between those two carbons. And then I did the attack in basic medium because the CN attacked the less substituted carbon. You need to be able to work backwards in case you are given your product and you're asked to go ahead and find your reactants. Let's go ahead and have another example now of an epoxide locked in a cycle. So if I have a cyclohexane and I have my epoxide locked in a cycle being at the back, okay, and this hydrogen or this CH3 is in front. And I am reacting this with ammonia. Ammonia is a base. This is going to be my first step. And my second step, I am using water. So again, you look at the first step in here and see there is no acid. So it is going to be a basic medium. Basic medium means that your base or your nucleophile needs to attack from the opposite side of the leaving group, and it has to attack the less substituted carbon of the epoxide, which is this guy over here. This is partial positive. When it attacks, it's going to break the bond and form a negative charge on the oxygen. Now notice now that your epoxide is locked in a cycle, so there is no free rotation. Before, there is a free rotation in there when you broke the bond between the carbon and the oxygen. There is now a free rotation here. But here, there is no free rotation in there. So this is why it's locked in a cycle. So stereochemistry is now very important when your compound is locked in a cycle. You keep your stereochemistry, and your stereochemistry is always retained. So now the oxygen that was once belonging to the epoxide now is going to have the same configuration as the oxygen of the epoxide. So it's going to be behind, same as that one of the epoxide. I didn't change the position of the CH3 in there, but the NH3 attacked from the opposite side of the leaving group. So now the NH3 needs to be shown in front, not at the back or not in plane. It has to be in front. Now, because the nitrogen now made 4 bonds, it is a plus charge. Please do the plus charge. Now, in these types of reactions, by the way, you don't need water because you can do simple hydrogen shift with these reactions. It's within the molecule itself, so you don't need to introduce water in the reaction. You can do an H shift in there, and especially when you have an acidic hydrogen and a base in here from the lone pairs on the oxygen within the molecule itself. So the base now is going to come, take that acidic hydrogen and form a lone pair on the nitrogen. So the NH3 is going to add in a form of an NH2. But notice, like my product now, it is a trans addition. And it's not a cis, it is always a trans addition in this case. So you're going to end up getting your CH3, and the addition here is going to be trans with respect to the NH2 and the oxygen. They are on opposite sides. Your nucleophile can never attack from the same side of the epoxide, or else it will not be able to break the bond of the epoxide. Let's have another example over here. So if I have, still we are working with a basic medium. So if I have something like this, and I am reacting this with, let's say, Grignard, or let's be more specific in there. So let's do a CH3, CH2, and MgBr in presence of an ether, a diethyl ether in there, and then the next step, I am using water. So you look at your first step to decide what type of medium you are working with. And I know that the CH2 over here is the one that is connected to the magnesium. So this one is going to be my nucleophile in this case. There is no sort of an acidic hydrogen in here, no acid involved. So this is going to be a basic medium. So the base is going, whenever it attacks, it's going to attack the less substituted carbon, and it's going to attack from the opposite side of the leaving group. If the leaving group is in front, then the attack is going to be at the back. So the CH2, CH3 is going to be at the back. And then the oxygen still retains the same stereochemistry of the epoxide. And then, of course, I do have my ethyl in this case. This is going to be a negative charge. And then my next step is going to be the addition of the water. This is step 2. So you're going to go ahead and do the protonation, and you're going to end up getting the trans addition. So you're going to have your trans addition. This is an example of an addition reaction. And here you go. So you're going to have your trans in this case. And the trans is going to be between the ethyl group and the OH. Now let's have an example in presence of an acidic medium. Let's do it locked in a cycle again. Here you go. And I have my ethyl group in here. And I am reacting this in presence of an acid. Now, the first step needs to show that you are working with an acid. Any acid can do the job. And the acids that you can use are, actually, they are limitless. Because the acid that you want to use also needs to generate a nucleophile. So you cannot just use H2SO4. because H2S4 cannot generate a nucleophile. If you want to use H2S4, you have to use water with it. So the types of acids can be either HCl, HBr, you can use HI, you can use HCN, you can use water in presence of H plus. And the H plus can be any acid, like sulfuric, phosphoric, any of those, because we know that when water reacts with, let's say, sulfuric acid. So when water reacts with the sulfuric acid, this is the acid-base reaction in there, then you're going to end up having a base with the acid. So you're going to end up getting your H3O plus. So this is going to be the hydronium ion. And the hydronium ion is an ion that is always produced whenever water is coupled with any form of an acid in there. Okay, so these are the types of acids that we are going to use in the reaction. Now, the idea here, the reaction is going to proceed by forming different products than that of the basic medium. The reason why is because of the mechanism of the reaction. This is acidic. It is not basic medium. And you do have an oxygen with a lone pair. So always in acidic medium, the first step is the protonation of the oxygen, because you want to protonate the oxygen in this case to allow the bond to be broken, and you can have the oxygen to leave. So the first step is you protonate the oxygen by simply reacting the oxygen with the partial positive charge. This is going to be my nucleophile, and it's going to react with the electrophile of the hydrogen, and the CN over here is going to leave. See, that CN is a good nucleophile that is going to attack, similar to all of these nucleophiles in there in the reaction that proceed, that allow the reaction to proceed by a simple nucleophilic attack. So the CN is going to leave, and what you're going to end up getting here is a protonation first. So you need to show the protonation step here, where the oxygen is being protonated, forming a plus charge, and then keep the stereochemistry. So that is going to be my first step of the reaction. This is an ethyl group. So this is going to be the first step of the reaction, which is going to be step number 1. I didn't do this step in the basic medium. In the basic medium, the base immediately, or the nucleophile, immediately attacked the less substituted side. But in the acidic medium, it cannot, because your nucleophile is the CN, and your nucleophile is locked with the hydrogen. So you need to break the covalent bond to release the CN so that it can attack. To do that, you need to protonate the oxygen. So we did the protonation of the oxygen. Now, this oxygen is plus charge, and the rule says that whenever you have a cycle and one element in the cycle has a charge, then this charge needs to be distributed over every single element in the cycle. This means that this carbon over here is going to be a partial positive, and this carbon over here is going to be a partial positive as well. Because now the plus charge will not be just focused on the oxygen. You want to make your structure stable. To make it stable, you have to distribute the charge. The charge should not be located just on one element. So to distribute the charge, you distribute it over all the elements in the cycle. So now each one of those are going to be partial positive. So each one of these carbons is going to behave kind of like a carbocation. It is not a carbocation, but it will behave like a carbocation. We know that more substituted carbocations, which are tertiary carbocations, are more stable than secondary than primary. So here you're looking at the more substituted carbon with a plus charge, which is this one over here. So in acidic medium, always the nucleophile, because what you did here, you freed your nucleophile. This is the CN minus, you freed that. So now the nucleophile is going to come and attack the The most stable carbon, is the carbon which is the most substituted. So in acidic medium, the nucleophile is going to come and attack the most substituted carbon to open the bond, but still it's going to attack in the same way, in the same stereochemistry in there, where it's going to keep in mind that the attack is going to be from the opposite side of the leaving group, always, because your epoxide is locked in the cycle. And you're going to end up getting over here. So you're going to get your product right away because you did the protonation. Your OH is now having the same stereochemistry as the epoxide. The epoxide is up, your OH is up, but now the attack of the CN is going to be at the back. So you're going to end up having your CN at the back. That is going to push the ethyl group to be in front. Okay, and you're still going to get a trans addition in this case with respect to the OH and the CN. Both are going to be trans, but the CN is going to attack now the most substituted carbon because that carbon behaves more like a carbocation-like. Let's have another example here. Okay, so if I have something like this, and if I have my epoxide, which is up, okay, and I am reacting this with water in presence of H2SO4, hydronium ion. So these two are going to form the hydronium ion in there. This is going to be your acid, okay? So the first step is going to be the protonation of the oxygen. This is going to be the nucleophile, and the hydrogen is going to be the electrophile. So the lone pairs on the oxygen are going to come, they're going to take the hydrogen, and the oxygen is going to add lone pairs and leave. My arrow here needs to be on the, so the electrons are going to add to the oxygen in there, and water is going to leave. So you are going to end up protonating the oxygen and releasing your nucleophile, which is the water. Okay, so this is it over here. Put the hydrogen there, plus a charge, and let's put the others. Okay, plus you have your water in there, which you released. So water now is going to be your nucleophile in this case. And as we mentioned, both of these carbons are going to be partial positive. This is a more substituted carbon. So now the nucleophile is going to come and attack this carbon and open the bond. So you are going to end up having the oxygen over here that is coupled with the hydrogen. So this is going to be your OH over here. Okay. And then I'm going to end up having my 2 CH3s in there. And then my water, it's going to attack. Now the water is going to attack from the back, but we agreed because this is a carbon single bond carbon, you don't need to show any of those stereochemistries in there. Whether the OH is in front, the water is at the back, because you have a free rotation around the carbon single bond carbon. But I'm going to go ahead and show that so that you won't forget that you need to consider stereochemistry if your epoxide is locked in a cycle. And always your nucleophile attacks from the opposite side of the epoxide. Now, I cannot say that this is of my product because I have a plus charge in there. So what's going to happen is that if there's any base in the solution, then that base is going to come and pick that extra hydrogen. We do have a base. We do have two types of bases. We have water to be a base, and we have the HSO4 minus that left from the H2SO4. This is another base. So pick any of those bases in there to come and take the acidic hydrogen. So I'm just going to pick this base over here. This base is going to come take the hydrogen, add a lone pair, and now my product is going to be a di-O. So I'm going to end up having my OH over here, and I'm going to end up having my OH over there, and this is going to be my final product. There are more practice problems in the problem set. Please practice those.